this is the Analytics 1 lecture for continuous distributions. Our learning objectives and new content here are going to be focusing on the distinctions between discrete and continuous random variables, thinking about how to represent probability graphically, and making applications to both the uniform and continuous random variables. Uniform and normal random variables. We're also going to talk about z-scores. In terms of our vocabulary, we're going to go to continuous random variables, uniform continuous, and normal random variables, and then we're going to finally talk about the standard normal distribution. We'll talk about ways of calculating probability and percentiles using Excel by using the norm.dist and norm.inverse functions. All right. Let's take a moment here and talk about the distinction between discrete and continuous random variables. Now, in discrete random variables, all of our outcomes were integer values. We were thinking about things like the number of sales that someone might make, 0, 1, 2, 3, 4, 5. For a continuous random variable, we need not have an outcome that is limited to these integer values. And so that could happen in two ways. Either we're looking at things like miles per gallon, which is not necessarily discrete by its very nature, or something where the numbers get so big that the value of counting the probability for any one of the individual values is too small, like the number of web page visits Amazon gets per day. Whether that's 1 billion or 1,000,000,001, the change in that outcome is so negligible that we can approximate it as a continuous random variable. So let's talk about an application to the uniform random variable. We're going to look at the example we dealt with in our previous lecture on discrete outcomes, where we were looking at our mechanic problem. So we've got our mechanic that has an opening, their schedule is wide open tomorrow from 8 a.m. to 4 p.m. And we want to know the probability that we're booked at exactly 8 a.m. So we're going to do the same steps. I'm going to define a random variable that represents the appointment time. I'm going to write the event as the time slot that is selected for me is 8, x equals 8. As I've stated, this is going to be a uniform random variable, and now we're going to talk about how we would actually calculate the probability that x equals 8. All right, since you've seen this for discrete before, this should be nice and straightforward. We've got 8 possible events in our sample space. All of them are equally likely, which means we can write our total set of events for which we know the sum of the probabilities has to be 1 as 8 times the probability that any one of those events occurs, or 8 times the probability that my appointment is 8 is equal to 1, which gives me a 1 in 8 chance of seeing an appointment time at 8 a.m. To get the idea across of what the difference is between a discrete and continuous outcome, what we're going to do here is we're going to think about dividing the appointment times into smaller and smaller and smaller units so that we could think about what happens as the limit approaches infinity. If we could continue dividing the possible appointment times from hours to minutes to seconds to microseconds, etc., what would our calculation be here for the probability that we observe an appointment at exactly 8 a.m.? All right, so if we did this at the minutes level, we would see that during an 8-hour day, there are 480 possible time slots. If each one is equally likely, then my chances of getting a spot at exactly 8 a.m. are 1 in 480, or 0.21%. If we were to do this again, but at the second level, we would have 60 seconds per minute, 60 minutes per hour, 8 hours a day. That's going to give me 28,800 seconds that I could have my appointment scheduled. Each one is equally likely. That means the probability that I have a time slot at exactly 8 a.m. is 0.0035%, or 1 in 28,800 seconds. What we can see here is that as our sample space becomes infinite, as this becomes more akin to a continuous random variable, the probability that we see an appointment slot at exactly 8 a.m. goes to 0. Okay, it's as if we were saying if there are infinite possible numbers that we could pick between 8 and 4 p.m., the chances that any one of those numbers is selected goes to 0. We can see this visually by representing probability in terms of the area under our probability distribution function. So remember here, our basic rule for probability is that the sum of all of the events, the sum of the probability of all of the events has to sum to 1. Okay, something has to happen. And so what we could do here is we could represent graphically our the probability of observing any event by creating some sort of little rectangle here that represents the event we're interested in. So we know there are, in this first case, 8 possible events, 8, 9, 10, 11, 12, 1, 2, or 3. Each one of them happens with equally likely outcome, which means for the area of this to be equal to 1, we would have the height of this probability distribution function would have to be 0.125. So that when I look at the likelihood of having an appointment here at 8 a.m., this is a 1-hour time slot. The height is 0.125. This is a 1 in 8 chance of getting this particular time slot. If we were to break this down into a minute by minute level, the height of this is still the same. However, instead of having a full 1-hour block here for the width of our rectangle, it is now 1/60th of that hour. And so we could similarly calculate the likelihood of getting an exactly 8 a.m. time slot by saying 0.125 times 1/60. And finally, if we were to look at this this outcome where we could have an appointment scheduled every second, we would see that instead of having the width of our little red rectangle be 1 hour or 60 minutes, or in this case, 1 minute out of the period, it is 1 second out of the possible 3,600 seconds that could take place at 8 a.m. So the width of our rectangle here would be 1/3,600. The height is 0.125. And when you multiply those two things together, you're going to get your 0.0035%. So that's all we're going to end up doing here for every one of our problems going forward, is we're going to think about how we can represent probability statements in terms of the area under a probability distribution function, as opposed to thinking about the probability of observing any one individual outcome. So to make this clear, I'm going to describe for you how we're going to write probability questions going forward using inequality statements rather than something like exactly equal to. Here, we're going to say, what is the probability that we get a time slot before 9 a.m.? So let's go back to our first example here where we have hourly appointments. There are 8 events. Only one of them satisfies the criteria that the time slot is before 9 a.m. That means the probability of getting a time slot before 9 a.m. is 1 in 8. Similarly, if we were to look at the minute by minute possibilities, we see that there are 480 events during the day. 60 of those satisfy the criteria that the event is before 9 a.m. So my probability of seeing an event before 9 a.m. would be 60 out of 480, or 1/8 again. Finally here, if we were to do this second by second, there are 3,600 seconds before 9 a.m. for which there's an opening. There's 28,800 seconds total. Again, the probability of observing an event before 9 a.m. ends up being 1/8 here. So what we're going to be thinking about here, again, going forward, is we can represent all sorts of interesting probability statements in terms of the range of values we could observe for an outcome. And that's going to be a more appropriate way of tackling these for a continuous random variable than asking about the probability of observing an exact outcome. We're going to now turn to the most common distribution we're going to use for the remainder of the class here, which is the normal distribution. Now, the normal distribution looks very familiar, I'm sure, to most of you. It's what we would think of as a bell curve. And it has a few properties that are worth discussing right off the bat. So the first property is that the normal distribution is symmetric around the mean. So a random variable x here is always going to be symmetric around its mean. The mean is going to be equal to the median. And I'll read this statement for you. It says the probability that our random variable x is less than or equal to some value x0 relies only on what that value x0 is, what the population mean is, and what the population standard deviation is. And we would call this mean mu, and the standard deviation here is sigma. So for example, I could say, what is the probability that my random variable x is less than or equal to mu, the mean? I would write this in the following way. I would say, what is the probability x is less than mu? And since we know that the mean is equal to the median, the probability of seeing something less than the median is 50%. All right, so that's what we're going to be doing here, is we're going to be trying to write out the problem we're interested in, and I'm going to encourage you to graphically kind of shade these areas in as we go through these problems. So let's just go through a couple more examples here. Suppose that our test scores are normally distributed around a mean of 70 with a standard deviation of 5. The first thing we're going to do is draw a bell curve here, draw a normal distribution where the mean is 70, and we're going to delineate things in terms of standard deviations here. So every 5, I'm going to put a tick. What is the probability that we see a test score less than or equal to 80? Well, this is just everything from 80 on down. We could write this in terms of the three pieces of information. X0, our threshold value of test score, the mean, and the standard deviation. Similarly, I could write a question, I could similarly shade in a region on a graph that corresponds to seeing a test score of at least some value. In this case, we're going to say, what is the probability of observing a test score that is at least a 65%? And we would again shade in the area that is above, in this case, our threshold value 65, noting that our mean is at 70 and the standard deviation is 5. So we can see that this represents the area to the right of 65. Finally, there will be times we might want to be able to calculate the probability of observing an event where that event is between some range of values. And so here we might be asking, what are the chances that somebody scores between a 65 and an 80 on a test? And so we could shade this area in here. This is the range between 65 and 80. Now, the caveat with the normal distribution as compared to the uniform is that we're not going to be able to calculate the area of some probability, the area corresponding to some event arithmetically, because we're not going to be able to use rectangles in the same way we would for the uniform distribution. So for the uniform distribution, our probability distribution function is a rectangle, which means we know how to calculate the area under a rectangle pretty easily. But since the normal distribution is bell-shaped here, calculating the area under that curve would require us either to calculate an integral, which is beyond the scope of this course, or to use some sort of technology to help us out here. So what I'm going to do is talk briefly through how we could use Excel to calculate this. So for any random variable x, if we had a statement that says find the probability that our random variable is less than or equal to some value x0, we're going to use the function norm.dist in Excel, and it's going to take on 4 arguments. First is Excel is going to write this as x, and this corresponds to x value, x0 in our problem. The next is the mean, mu. The next one is the standard deviation, sigma. And finally, in our situation here, we will always use true for the argument cumulative. All right, so let's take a look at how we would actually implement this in a couple of examples here. Let's go back to our first example on the likelihood of seeing a test score less than 80. Well, we said the 3 pieces of information we would need are the threshold value of our test 80, the mean 70, and the standard deviation 5. In terms of what we would plug into Excel, we would simply say this is equal to norm.dist of our threshold value 80, population mean 70, and the standard deviation 5. And we always plug in true here for the cumulative argument when we're dealing with continuous random variables. And that turns out to be a 97.7% chance that somebody scores below an 80% on this test. Similarly, we're going to try and calculate the probability that somebody scores at least a 65%. Now, recognize that our norm.dist function is defaulted to calculate the area to the left of a point. That is the probability that we would observe a test score less than or equal to 65. So in order to get greater than or equal to it, what we're going to have to do is rearrange the expression using our 1 minus trick that we implemented in our binomial distribution applications, where we say that the probability of seeing a test score above 65 is 1 minus the probability of seeing a test score below 65. And so we can then plug into Excel 1 minus norm.dist of this threshold value 65, the population mean 70, the standard deviation 5, and again, for the cumulative argument, we're going to put true. This is going to give us an 84.1% chance of seeing somebody score at least a 65% on this test. Finally, when we're talking about calculating the probability that our test score falls in a range of values here, we're going to also have to rewrite this question in terms of the cumulative argument. That is to say, since we want to get the area between 65 and 80, one way of thinking about this visually is to say, well, we could take the area to the left of 80 and subtract from it the area to the left of 65. So when we see that our Excel function requires us to write our probability statements in terms of the area to the left of a point, this is going to be our only option here. Okay, so I could write this problem as the probability x is less than 80 minus the probability x is less than or equal to 65. And that would just be norm.dist of 80, 70, 5 true minus norm.dist of 65, 70, 5 true, or 81.9%. And we'll see all of these are different ways of representing different types of problems here. We're going to practice every time shading them, every time figuring out what the appropriate probability statement would be here in Excel. Occasionally, we may want to know one other piece of information related to the normal distribution, and that piece of information is the percentile for a particular, the value of a random variable at a percentile in the distribution. So suppose I wanted to know what the 80th percentile of test scores would be here. So I've decided that if you get at least the 80th percentile in your class, you automatically get an A. So what test score do I need to look out for to make sure that everybody who got at least that test score gets an A? That's a norm. That's a slightly different question for the normal distribution. So let's take a look at what we're actually after here. What we're after is going to be solved for us with the norm.inverse probability statement. Excuse me, the norm.inverse function in Excel. And the way we're going to tackle these is to identify the area to the left of some point, here shaded in pink, the mean and the standard deviation of a distribution. And that's going to return for us the value of x such that some percent of the data are to the left. So here, again, we need to know the area to the left, the mean, and the standard deviation. So if I were to ask, what is the test score at the 80th percentile of the distribution, I would say this is equal to norm.inverse of 0.8, 70, 5. And that would turn out to be a 74.2. So on this particular test, if you scored a 74.2% or higher, you would be above the 80th percentile. Here's an example of when you might use norm.dist versus norm.inverse. The formal statement is here. On the left-hand side, this is going to be an application for norm.dist. And to identify whether you're going to be using norm.dist or norm.inverse, you just need to figure out, am I trying to calculate a probability? And if that's the case, I'm going to use norm.dist. Or am I trying to find a value of a random variable? And that's the case. If that's the case, we're going to use norm.inverse. So for example, on the left here, I'm going to say cars get an average of 30 miles per gallon with a standard deviation of 2 miles per gallon. What is the probability a car gets under 27 miles per gallon? That would be, what is the probability x is less than 27? This is a norm.dist question. Conversely, if I were to ask, how fuel efficient is the car at the 95th percentile? That is, what is the miles per gallon I can expect out of a car at the 95th percentile? That's a question where we're saying, I know the area to the left of a point, but I want to know what that point happens to be. Here we would say this is norm.inverse of 0.95, 30, 2. To clarify how we think about norm.dist and norm.inverse, I'm going to give you 3 examples here where you're going to determine whether you should be using norm.dist or norm.inverse to answer these questions. So we've got Luca, who's out selling something. On average, he sells $500 worth of stuff every day, and the standard deviation of his sales is $25. And we know his sales are normally distributed. What are the chances he sells more than $600 worth of stuff in a day? Again, here we know the value X that we're after, and we're asking about a probability. So we're going to use norm.dist here to calculate this. Now, since we want to know the probability he sells more than something, we have to remember to use our 1 minus norm.dist trick here to get the area above something, since norm.dist always automatically calculates the probability of observing something less than or equal to a particular value. Our next question says, how much can he hope to make if he's at his worst 25% of days ever? Here we know that we are at the 25th percentile of days, but we don't know the value of the random variable x, that is how much he will actually sell if he's at the 25th percentile. So we're going to use the norm.inverse function. Finally, how likely is it he sells between $400 and $500? This again will be a norm.dist question because we know the value of the random variable x we're after, but we need to figure something out about a probability. The last topic I'm going to touch on today is the standard normal distribution. And the standard normal distribution is just a specific type of normal distribution where the mean is always 0 and the standard deviation is always 1. Sometimes we refer to this as the z distribution. And the z distribution is a very useful distribution to think about precisely because every single normal distribution problem you ever think of tackling can be rephrased in terms of a z distribution. And so that makes it a very easy distribution to become familiar with because it's going to relate to almost every problem we're going to tackle from here on out in the class. And so the way of turning your problem into a z distribution problem is to convert your data into a z-score. And a z-score is, the formula for a z-score is given by this simple expression that says, I want you to take the data point you're after, subtract the mean, and divide by the standard deviation of that distribution. In words, a z-score is simply a measure of how far a data point is away from average in its own distribution. And the units are in terms of standard deviation. So more simply, it's the number of standard deviations a value is away from the mean. If the z-score is positive, it means it's above average. If it's negative, it means it's below average. This is our standard normal distribution. Again, we're going to delineate this with the variable z. It's going to be at a mean 0, and all of our values are going to be written in terms of standard deviations away from 0. So let's go through one or two quick examples here where we can think about what a z-score is actually telling us. So we're going to find the z-score for a student who got an 80% on his test. We know that the mean of the test scores here is a 70 and the standard deviation is 5. Well, we're just going to plug these pieces of information into our z-score formula. X here is the student's test score 80, the mean is 70, the standard deviation is 5. We would say this student scored 2 standard deviations above average on his test. His z-score is 2. What is the probability that someone gets a lower score? Well, we could also calculate a probability statement here by using the norm.dist function, where we would say this is norm.dist of 2, 0, 1 true, or our value 2, the mean of the distribution for a z-score is always 0, the standard deviation is always 1, and again, we're always going to use true as a measure of for how to calculate things with a continuous distribution, because that's a way of saying cumulative, or we want everything to the left of our value 2. This problem should look familiar because it's one we looked at previously, where we asked what the probability was that somebody scored below an 80% on their test. We can see here that in that problem, we had the average, the mean here was 70, and the standard deviation was 5. So we can see here that if we move 1 standard deviation above average, you'd have a test score of 75. If you move 2 standard deviations above average, you'd have an 80%. And we can see that the area represented by test scores less than or equal to 80% is 97.7%, the same exact thing when we write that in terms of a z-score. One last problem here is we can use the z-score formula to rearrange and solve for unknown values of the underlying distribution. So imagine we had a student that was 1.5 standard deviations below the class average of 75%. The class standard deviation was 3%. What was the individual's test score? Well, we're just going to work our way backwards. We don't know the test score, but we know that they were 1.5 standard deviations below average, or their z-score is minus 1.5. So what does the test score have to be for them to be 1.5 standard deviations below average? Well, if the standard deviation is 3, then 1.5 standard deviations is 4.5 points below the average of 75. They would have had a 70.5% on their test. I would like you to take a look at some homework problems you'll be able to find and submit directly into Moodle, and those will be due by the end of the day on July 27th.